Welcome everybody to another edition of Shape Shorts. Our final episode in the I-6 is applied to the humanities and the sciences. You've had to listen for the last few times to Tony Patuco talk about time, space, and you took a lot of time doing it, and some of you occupied a lot of space. Well, now we're going to see what precisely is occupying that space. And when Tony shows up here, by the way, we didn't let him go home. I want everyone to know he didn't go home, so we don't have to chase him down and argue about what time it is. Anyway, Tony.
Hey, Stu. Good to see you again. Well, today we're going to finish off today with I-6 with the idea of matter.
Right.
And the stuff of the universe.
Yeah, we're going to finish with...
So we'll do that in greater detail today.
Yeah, and you can go ahead and go over what mass or matter is.
Yeah, we'll discuss that. It's
going
to be kind of fun.
I didn't get a lot of sleep last night, so I think I'm going to take a little nap. You don't mind, do you?
Well, you always take a nap. When I start talking, you go to sleep right away. It's
you know what? The last time I didn't go to sleep, you know why?
Why?
I caught students sleeping, so I was snapping them in the back of the ear like this, because it's embarrassing for you.
We have students today, right? We have 3 students today.
Yeah,
okay,
3.
Good.
You
3?
can't count. See what?
Well,
why do I have to do this?
I didn't count you because you know.
No, it's 4 counting me.
Oh.
3 plus 1 is 4. That's called arithmetic. You're a mathematician, but arithmetic is still a mystery to you. Anyway, everybody, here's Tony to talk about.
Thank you, Stu.
Math.
Thank you. This is our last episode on the foundations of physics, trying to incorporate, again, what would be about 5 or 6 minutes into the first lecture of a physics class for physics majors or engineering majors and so on, where we try to get the students heavily engaged in the ideas of physics initially. It's not so much the picture that they're going to be dealing with the mathematics of physics and how we describe motion and the equations that we're going to develop and derive, the notion of certain laws of physics and so on will come naturally later on. But the foundations of physics are based upon 3 ideas, which we talked about earlier. The first one was space. The second one is time. The third one is what occupies that space, as Stu would indicate. What occupies space? And again, this is pretty obvious. Again, another idea that is commonplace, never questioned, it's just there. An object occupies space. It gives us a physical reality that something is there. It occupies something called space, which we haven't defined, and it can travel in time. I take a ball, an object, I throw it in space. It takes time to traverse a certain path, and again, the connection between space and time. But now, matter or stuff of the universe is there. And the question is going to be raised, what is this stuff? Now, this is an age-old question as well. We go back to the pre-Socratics because the pre-Socratics is a time period of about 600 BCE, roughly almost 2,800 years ago, where we have the idea of asking the same question. This was done by a set of philosophers that were before Socrates. Socrates is roughly about the 350 BC period, and prior to this, from 600 BC up to that time, many, many thinkers. Now, we've lost most of them. We lost most of their writings. But the pre-Socratics, as we call them, left a bit of, I used to call them tidbits of notes that were translated and retranslated and retranslated through history. Some only a few lines that we're able to translate. But they are dramatic in what they said. Now, they didn't address too much about time, although some did. They didn't address too much about space other than geometry, which they held to the beliefs of space being something that they had faith in, which would later be capitalized by Euclid and put into a geometric framework of these so-called common notions. When it came to matter, there was way too much of it. It wasn't, in a sense, time for everybody. It wasn't such a thing as space for everybody. every piece of mass, pebble, shell on the beach, every object that they saw was in effect a different object. It wasn't the same. Different color, different texture, different tactile sense to it, a softness, a hardness, a shape. Where do they come from? Certain trees had the same shape leaves, but the leaves were somewhat different, maybe in color or in size, but they were still very much different. But they occupied this thing called space. So as a result, the question, what is this matter, would be almost natural. There are many, many ideas floating around, but the one I'm going to focus on is an idea that what constitutes matter. Of course, matter constitutes matter. Yes, that's an assumption. It makes common sense. Obviously, if I have matter in matter, if I break a stone open, I still see stone inside. So it's not only making sense in that way, I can actually show it to you in that context. One pre-Socratic Democritus, at about 600 BCE, had come up with a rather remarkable idea, and that was based upon two fundamental Greek concepts. The Greek concept of ultimate division of mass. If I take a stone and I break it and I break it and I break it, I can smash every piece to its fundamental grain of sand, and I can smash that grain of sand to its fundamental piece, which is another grain of sand, smaller, and I can smash that one. And I can do this ad infinitum. I can do this until, in effect, every piece of sand can be subdivided, smashed, if you will. And that was basically called a tomos, the idea of continually cutting without stopping and coming down to anything more fundamental. Just continually cut and cut and cut. It got smaller. It, in essence, you might lose its visibility, but it still was there and could be cut further. In Greek, when you want to negate a phrase, you usually put an A in front of the word, and Democritus would say, no. This is an atomos, that I can indeed cut only to a certain point, and I will find the fundamental piece of all matter. This is a remarkable idea. At 600 BC, of course, atomos reduces today to the word atom, and we all know that phrase, that an atom is the constituent part of all matter. And we look very heavily into this. And this idea of an atom would be controversial throughout history. In fact, we lose it. It resurrects itself in a poem by Lucretius. And in 200 AD. It's a good thing Stu Barr's here. He'll always fix my dates. The idea that you would have Lucretius write a poem on the nature of things, as he called it, itself would disappear until a bookseller, and that's roughly Poggio in Italy, would resurrect this poem that Lucretius had written based upon the idea of Democritus, that an atom was the fundamental piece of all matter. This is remarkable. It meant that an atom, when pieced into its constituent part, didn't necessarily have the size, the shape, the color, the texture of that global matter. It was the building block of all matter, which meant every item that you see, regardless of its color, its shape, its size, its mass, its textile feel, if you will, softness, hardness, was solely dependent on these atoms that made it. This is a remarkable idea. This is not simple, but yet at 600 BC, you can fathom how can you possibly even show this to anyone. It became controversial. It wasn't in the context of commonsensical. And in our earlier discussions, we talked about space as commonsensical, yes. Time even still commonsensical. Here we go to matter, which is completely without the realm of common sense, out of the realm of common sense, because in effect, how do I get one little tiny Lego piece and can build almost anything with it that has a variation of color and, in essence, strength, shape, size, and so on, all made by that one piece. Well, this would be a controversial idea, as you can imagine. I cannot show you an atom. I cannot get there. It's too small, let's say. And as time went on in history, we find that the atom would not be literally accepted until late into the 19th century. And individuals would promote this idea over many, many years. And one thing I would do in class would, as an example, if I took a liter of water and a liter of alcohol and pour one into the other, I do not get 2 liters of a substance. I get a little bit less. And doing a demonstration in class is a simple one to do. It's a little hard to see the distinction, but you could do it with a nice volume and so on. It's an easy thing to do. But another thing I would do was I always had a bucket of pebbles and a bucket or beaker of sand. And I would have the weight or the volume of these pebbles in one beaker and another weight of the sand in another beaker substance, 2 different substances. Pour the sand into the pebble beaker, and you do not get twice the volume. You'll get twice the weight if you'll get the combination of the weights, that's true. But the volumes were not the same because the sand would slip through the pebbles. Very much the way if there were atoms in alcohol and were atoms in water, then maybe some of those atoms would slip through the other atoms like the sand which slipped through the pebbles. This is a remarkable picture, and you show that to students, and the first time you start to realize, wait a minute, that's basically true. How does this occur? How does this occur when in fact you have matter interacting with matter like liquids? Another example. Take a block of steel or a block of metal, and you heat it up. And we all know that hot objects begin to expand. And they expand rather large. And it could be dangerous. And bridges on railroad lines, when the expansion occurs in different hot periods of the summer. In a car, things begin to buckle. So, in effect, we knew that materials expand. Where does the material come from? If you're going to expand it, shouldn't there be matter in there? That's somehow more matter added in out of nowhere. So there were obvious things that became questionable unless maybe these atoms would link together, and when you heated them, they began to expand and making more space within the material. Again, space commingled with matter. So matter becomes our third most significant idea in all of physics because we study matter. And we need space to put matter in. The matter changes in time, whether it changes position or changes shape. Time, space, and matter become convoluted. And that's why you're here in physics, because those 3 ideas, space, time, and matter, undefined. I'm not defined matter. I haven't said what an atom is. And even today, as I go deeper and deeper into the atom, we're going to find either smaller and smaller particles within that matter, within that atom. And you'll all hear these great words, the quarks and the mesons and all the subatomic particles that you've heard of, the Higgs particle and so on. All these particles in particle physics, smaller and smaller and smaller, begin to identify we found the smallest piece of matter yet. And yet, even though I don't know what it is, I can measure it, I can talk about its size, I can talk about its mass, at times I can talk about its what we call electric charge, and all kinds of other things about it, the fanciness of the parity and all that kind of stuff about symmetries, but we won't get into that. But it's an exciting area that suddenly a commonsensical picture of matter becomes foundational in something I cannot really define, and we're still looking for it. So space, time, and matter become the foundation of physics. And to talk about these 3 items takes about 15 minutes in a classroom to get the students heavily involved in looking in their eyes, particularly when they're young and they're curious, because maybe they were never asked to find something like this before, and suddenly now they're challenged. Maybe what I've thought is not as obvious as I did think. And therefore, I hope to see you in my next physics class. Thank you.
All right, everybody, here we're going to see how the I6 applied to mass and matter.
Mm-hmm.
That seems kind of weird, but we're going to do it anyway. And I want to bring a couple anime. The whole idea of the water and the alcohol, I think, is fascinating for a student to see.
Yeah.
They appear to be two liquids, and if I have a liter of each, I should get two.
Right,
and you don't.
And you don't.
And
using a model of the sand and the pebbles, when you do that, you're going to look. Wait a minute, that makes sense.
But it doesn't make sense with the alcohol because
unless you're thinking, wait a minute, is alcohol the pebble and is water the sand, or which one is which?
Yeah.
So you get that idea. It's a hard experiment because it's such a minor amount, but the sand and the pebble do the job.
Yeah, and I think that was a good illustration of anime. Tell the story. The pre-Socratics, Democritus, and all that are very much a part of the story of the understanding of mass, the understanding of how I try to define the stuff of the universe. Mass, sometimes when doing this, I hate to use the word mass because to these people, it's stuff.
It's just. In fact, I never use the word mass.
Yeah.
The first day, I say it's just stuff of the universe. Of course, they come in with all this knowledge.
Yeah.
And I call it baggage from different schools, the colleges or whatever. And
Yeah.
They come in with the idea, I know what an atom is.
Yeah.
But do they really?
Yeah.
Of course, they came in with the knowledge of time and space as well.
Yeah, and that leads to the next one. So you have all this stuff. You're made out of stuff. What is this stuff? And that brought up something I think you brought up to kind of hint to. If it is atoms, how much space does an atom have, and how much space is in an atom? And how do I separate the two? Or are you mass or are you space?
Well, to give you some idea, the original idea about an atom, of course, it took many years to get this, was a nucleus, and surrounding the nucleus was a set of electrons. The space between the nucleus and the electron is immense.
Yeah.
When you come down to it, it's just gigantic amount of space. People think the atom is really condensed and everything. No, it isn't. It's mostly space.
It's empty.
It's empty, and so you have that part of it, but that comes with great experimental observation later on.
And it goes to the idea of trying to define what mass is.
And no, we don't.
And we still, just like the other two.
We say, this is a particle, it has these properties.
Yeah.
But yet, what is it?
Yeah.
I mean, other than the fact that we identify its charge and its weight, its mass basically, we know things about it, but what is it?
And the more we define it, the smaller it gets. The less we know. Actually, the less we know.
The less we know, and even today, we're not settled on what's called the standard model of physics. We're not settled on it. It has problems. We want the problems to disappear, but they're not disappearing. New ones come up almost every year, and the theory is beautiful theory. It's the most beautiful theory we've ever had, but it still has flaws, and we still have problems with it. So it is not really resolved today.
And I think you just brought up something people forget. I think what all of this does, you start to learn that, like the humanities I talked about in this, the sciences are fascinating. We get the idea that everything is answered. We live in a world where what we do, we don't really know too much of anything. And when we start to look at these, and I think that's a good example, when we see them with the humanities, and you brought it up with Democritus on the nature of things. Mm-hmm. When we see that, what we see is the very idea, the curiosity that leads to the sciences is often, and we've said it before, it's the same thing that we see in the arts.
Absolutely.
It's the world out there the universe out there is an amazing place that we virtually know nothing of. And we are always striving to try to learn more.
We gave a talk in, I think it was in Austin, where we brought, one of the discussion topics was, what motivated Lucretius to write the poem on the nature of things?
Yeah.
What's the motivation? What was that? What kind of curiosity did he have to bring it forth in a poem?
Yeah,
and then it disappears, of course, naturally. But imagine if Poggio, the bookseller, had not found it.
Oh, we'd be in a different world.
What world would we be in? And Democritus, that's 600 BC. Suppose they had taken it up as truth. And in that sense, where would we be today?
Change
So-
it. We're it's a very curious thing on there, and that goes back, like I said, rejuvenate. You just did it with the nature thing. Deus Ex Machina, different shapes. Look at matter. The very act that I have the thing called matter that almost seems to have an infinite possibility of shapes. Everywhere I look,
Right.
I see shapes. I may try to define why that shape is that way, but it's always secondary. I'm always looking at different shapes. Some shapes seem more common than others, but they're all made out of the same things. And why are there such variety?
Exactly.
And why is a sphere so common? And squares, I don't see too many in nature.
No, it's true. Spheres are very common, and yet the geometries that we have, the fundamental forms that we have, let's say, are crystalline in nature because of their atomic structure.
Right.
And that would be one of the first things you think of. Wait a minute, why does this,
Why do I get a crystal
and
and then a sphere?
And you break the crystal, you cut the crystal, and it fractures the same way.
Yeah.
And you think, maybe there is something.
There's something going on.
But it's fascinating to me that Democritus would actually think of this.
Mm-hmm.
And this is as fascinating as Bruno. Now, Bruno's much later. When he looks at the stars, and of course he gets
roasted.
He gets roasted on this one, barbecued on this one. and he says the stars are not on a celestial sphere. They're suns like our own sun.
Well, you
right
got to
here.
roast a guy for that.
These are tremendous answers that happen to be right with great curiosity. When you do that to a student, getting them going, these are not firmly understood. It's your challenge to begin understanding them. That's why you're here. You're not here to pass the class, and obviously you're going to do that, but you're here to extend the concept of humanity's understanding of the universe.
And before we close, I want to bring up something my grandmother used to tell me as a kid.
Grandmother?
Oh yeah. She was.
Yeah,
My maternal grandmother said, kids like to say they're bored. We never told her we were bored. That never worked. But she said, if you're bored, you look out the window and you look at nature and you look everything around you and you're bored. What's the matter with you as a human being? How could you possibly be bored living here? And I never forgot that, she didn't have much of an education. She came from Ireland with a 6th grade education. But when I would talk to her, she instilled in us that world is the most amazing, curious thing you'll ever find. And if you're bored, you really need to take a hard personal look at yourself, not at nature, because there's a problem in there. And I think whether we talked about the 6 humanities and the I-6 of humanities, the sciences, this is where they come together. Exactly. And if there's anything I can give people, it's not boring out there, people. If you're bored, you're not looking very carefully.
That's right.
I think you need to wake yourself up.
Not only not boring, it's exciting.
It's very
exciting. And in philosophy, when they taught that, we used to do the Aristotle walk.
Yeah.
Take them out into the environment and let them just look on the ground, pick up that stone, understand its weight, understand a little bit of its texture. Why is it? Where did it come from? How did it get there? It has a history. Far more interesting than your own, because it got there somehow.
Yeah, and you're not that interesting.
We know how you got here.
Yeah.
We know where you're going, maybe. But that stone has a history, just like yourself.
Before we close, I want to say something.
What's that?
Our director-producer told me something once.
What's that?
She took a class. She said, dig in the ground and look what's in there. I had never done that. Yeah. And once I started, I went, there's a universe in that ground.
Oh,
that's absolutely amazing.
Take a look at a blade of grass.
Yeah,
and just go deep into it and pull that grade out and look at the roots.
Yeah, look at the roots.
We used to do that with the Aristotle walk, was to get students involved and observe, identify, be mystified. And generate that curiosity. And that's the whole purpose of the I-6, is to pull in that curiosity. Because what is curiosity? The engine to creativity.
Right. And I think with that, folks,
thank you.
Thanks again, everybody.
See you next episode.
Okay.
Bye.